Now, hydration energy of alkali metals. As we go down a group from lithium to cesium, here is a considerable reduction in hydration energy. That is because of increasing size of atom from lithium to cesium that produces charge to radii ratio. Let's see first what is hydration energy. Hydration energy is amount of energy released when 1 mole of ions undergo hydration. So any 1 mole of ions that hydrolyze in water, the total energy released during that process is called hydration energy. Here we see, let's say for example, sodium ions. They undergo hydration in aqueous media and releases energy. That energy for 1 mole of sodium ions is called hydration energy for sodium. Let's clarify it further. We know first sodium will exist as a solid. So first step is atomization, in which solid sodium is converted into sodium atoms. So first step is total conversion of 1 mole of solid sodium into 1 mole of sodium atoms. This is atomization. Next step is we having in our sodium atoms. We convert these sodium atoms into ions. That is ionization energy. Converting 1 mole of sodium atoms into 1 mole of sodium ions is called ionization energy. Further, next step is hydration of these sodium atoms. These sodium cations undergo hydration with water molecules to release hydration energy. So there are 3-step process from solid sodium to hydrated sodium cations or aqueous sodium ions. So this is how the hydrogen and the LP is explained, and it is least for cesium, highest for lithium. Now, as I explained to you, charge to radius ratio. Here, going from lithium to cesium, atomic size increases. The metallic radii increases with going down a group. This will in turn affect charge to radii ratio. We know in all the alkali metals, charged cation will be unipositively charged cation, means having only a single unit of positive charge over atom. So with increase in radii, charge to radius ratio will reduce. Further, next property is melting points of these alkali metals. What we just saw, atomic or metallic radii here reduces down the group, increases down the group, which means, and what we saw here is melting points reduces down the group from 454 for lithium, 371 for sodium, 336 Kelvin for potassium, 312 for rubidium, 302 for cesium. So it is consistently reducing from lithium to cesium. And here we see atomic or metallic size consistently increases down the group. So what is the correlation between these two? The correlation is smaller the radii, greater the attractive force between the atoms, greater the force, higher will be the melting point, because more energy will be required to overcome such attractive forces. Thus, melting points will be higher in such a case. So, for alkali elements with smaller metallic radii having higher melting points, that's just we saw. This is smaller radii having higher melting points. Bigger radii will have lower melting points because attractive force holding the individual metal atoms together is weaker here compared to smaller metal atoms. Same thing goes to the boiling points. Next important property of alkali metals is standard electrode potentials measured in volts, denoted by E naught. Let's first solve. For lithium, we see it is a minus 3.04 volt, minus 2.71 for sodium, potassium having minus 2.92, 2.93 for rubidium, cesium just approximately the same, 2.927. So these are almost similar, last three elements having almost similar standard electrode potentials. Sodium having the least standard electrode potential among these alkali metals. You remember, more negative the standard electrode potential, better reducing agent it is, because when it having a higher negative standard electrode potential, it can easily donate electrons for the reduction of any other element or group. Now, let's first try to explain why lithium having the highest standard electrode potential among the alkali groups. Or if you consider it from with a negative sign, we should say why lithium have the lowest standard electrode potential among the alkali groups. Let's see. It can be explained using the properties ionization energy and hydration enthalpy. You see here, both ionization energy and hydration enthalpy for lithium is fairly high compared to other elements. But if you see, here it is not that big different. But for sodium, you see, ionization energy is far greater than its hydration energy, while for potassium, it's again different, but here is a comparison. If you draw it, it is slightly lower than this sodium. Rubidium, again, it is strikingly different. Here, 100 units different. But for lithium, we see it is almost close. So here is the three phenomena we just discussed earlier. First step is conversion of metal into metal atoms, gaseous state. These gaseous atoms ionized second stage, and these ionized atoms or ions get hydrolyzed to make aqueous ions, and these aqueous ions, this step is called hydration enthalpy. So the total standard electrode potential is combination of these three. The better this combination, or that makes the reaction spontaneous, means that if the total energy here, the total sum is making the reaction spontaneous, the standard electrode potential will be higher. And for lithium, we saw here, it is almost similar. While for sodium and potassium, this is having certain differences. That is the reason a standard electrode potential for sodium is not as low as in case of lithium. And for potassium, still this combination is, these three processes combination is better. In the summation of sublimation enthalpy, ionization enthalpy, and hydration enthalpy is making the reaction better or more spontaneous than sodium case. So that's why this having a still low standard reaction potential than sodium. For the rest of the two elements, it's almost similar to that potassium. So potassium, rubidium, and cesium having nearly similar standard electrode potentials. And for the same reason, we can assert that lithium is strongest reducing agent due to its very high hydration enthalpy compared to its ionization energy. So lithium is strongest reducing agent because its hydration enthalpy is very high compared to its ionization enthalpy. Now let's talk about the chemical properties of alkali metals. The alkali metals are highly reactive due to their large size and low ionization enthalpies. Here we have given just rough size of that elements. You compared to manganese, potassium is much bigger in size. Rubidium, you see, is largest in its own period. Cesium, similarly, fairly large size compared to all other elements in the same its period. For these reasons, low ionization enthalpy and high atomic size, this combination makes alkali metals highly reactive in periodic table. First alkali metal, lithium. Lithium have certain anomalies in its behavior. Like you see, it's having a fairly small size. Lithium ion compared to sodium ion and potassium ion. This anomalous behavior is attributed to its exceptionally small size. That's what we see. Because of its small size, it got high charge to radius ratio. Because of high charge to radius ratio, it got high polarizing power, meaning it can distort the electron clouds of anions or counterpart ions. You see, the anion electron cloud is distorted completely by the lithium ion